So for this week we're going to be talking about a few aspects of stellar evolution that we haven't really got into yet, including different types of supernovae. So here I've got, this is not a great image here, but these are different types of supernovae, and so we basically classify them into type 1 and type 2. And here it's a good idea to remember that a lot of the things that we do in astronomy, our naming conventions come from somehow that we classify them observationally, which may later prove not to be the best way to think about it. So a good example of this is the stellar classification, which was ABCD because it was based on hydrogen line strengths, and then we got to understand that it was a temperature sequence, and so it's OBA, etc., etc. And here again is another example of that, where it's basically down to the spectrum and what sort of lines you see. So it's do they have hydrogen lines, absorption lines in the spectrum? The type 1s do not, and the type 2s do. And that's basically the difference between them. So you go to supernova, you take spectrum of it at peak light, and you see a hydrogen line, then it's type 2, and if you see no hydrogen lines, it's type 1. And then the type 1 has different subclasses. Type A have silicon lines but no helium lines. Types 1b and C lack those silicon lines. And then type 2 has two subclasses, and that has to do with the shape of the light curve. So for the type 1, we said there's three subclasses. Type 1a have the silicon lines. So here you can see this is a spectrum in the visible. So this is red here, blue over here. And here's this silicon, it's an ionized silicon line in the type 1a, which is not seen in the type 1c. The 1b has a helium line, but no silicon line. One of the things that's notable is that type 1a supernovae are found in areas of galaxies where they're associated with old stars, slowly evolving stars, stars that are like the Sun, stars that have gone through an AGV phase, etc. Whereas the type 2, the type 1a, and the type 1b and the type 1c are all associated with star-forming regions, with places where there are lots of massive young stars. And so this really is some evidence that the type 1a's are different than the type 2's, 1b's and 1c's. And what is the most logical conclusion to draw from where we find them is that the type 1a's are low mass. Then how do they go supernova? Well, we'll come back to this, but one of the things that's interesting is that if we look at the spectrum over time, so this is actually looking at the spectrum of a 1b, and this is a 1a later on, and you can see they're quite different in the elements that you're seeing in the spectrum. Okay, so as I said, normally we think of supernovae as being associated with the core collapse of a very massive star, but there's another alternative that we can cause a supernova collapse, and that's in a binary system. And basically what you've got is you've got a white dwarf with a companion, and material flows off the companion onto the white dwarf, and in doing so it causes the white dwarf to exceed the Chandrasekhar limit, and it undergoes a thermonuclear explosion, and so we go supernova. But in this case, whereas the massive star will leave behind a neutron star or a black hole, it leaves behind the core, what was in the core of the star, only the outer layers are thrown out. In the case of blowing up a white dwarf, we have nothing left. It's entirely obliterated. And so some of the evidence that comes to this has to do with the lack of hydrogen or helium. So type 1a have no, remember all type 1s have no hydrogen lines. Type 1a also don't have helium, and they have these silicon lines. And so the idea is that you can explain this, that if you've got a white dwarf, then you've already lost most of the hydrogen, most of the helium prior to the explosion, whereas a star that undergoes supernova collapse still has some of those outer layers that haven't yet fused, so they will have those hydrogen lines and helium lines. And so because you don't have those, then you've stripped them away. So that's where the idea comes from, that you have a white dwarf. And so what you've got is a white dwarf in a binary with something that's probably a red giant, and what happens is that material flows from the red giant onto the white dwarf. We'll get into that in more detail in the next segment. And that influx of material, it's material that's flowing onto the star, and it is gaining kinetic energy as it's accelerated under gravity, and so it provides energy to the core. Remember, the core is degenerate, and so that heat is conducted through the core very fast, and so what you get is that the temperature rises in the core and carbon can fuse. But what that means is that you get a carbon flash. Just like we had a helium flash, you've got a carbon flash that once you switch on ignition in one place in the core, the whole thing is going to switch on very fast, and that's why the whole thing blows apart. And that's why you get such a huge brightness change. It's the carbon flash. But it's also where the majority of iron is made. We do make iron in more massive stars, but actually most iron is made in this explosion. Whereas most of the iron that's made in a core collapse star it gets destroyed in the photodisintegration, but it's in the neutron star or black hole. So most of the iron comes from the obliteration of the white dwarf in a Type 1a supernova. So we're just completely destroying a star. Now, we've already talked about this when we talked about the distance ladder. Type 1a supernovae have a characteristic light curve. So basically here I've got time in days, and I've got this luminosity. And you can see that Type 2s and Type 1s are similar in luminosity, but a Type 2 has a different shaped light curve compared to a Type 1. And it's the shape of this light curve that we can use as a standard candle, which I'll come back to in a second. What we find is that when we explode the star near maximum luminosity, so right at this peak, we've got these elements that are appearing, and they've been made in the explosion: oxygen, calcium, and magnesium. But then we keep watching it, and months after the explosion has occurred, we see that there are these other lines that are appearing, and we see iron and cobalt, and those are the things that are being formed as a result of the explosion. And so what I want to show you is this light curve. So here I've got, we're going to see the explosion of a Type 1a supernova in here. We're going to see how its brightness changes in this graph, and we can see how its spectrum changes in this graph. So here you can see it goes up in brightness and down again. And we're going to watch it again and see it is, if I can make it work, there we go. You see, there it is, it goes up in brightness and back down again, and that's the supernova right there. And finally, one more time, we're going to watch, you see how the spectrum changes quite significantly as the thing is cooling off. So we've got this light curve, but we can understand it in terms of the contributions of things that are being made. So what happens is you have an explosion that causes there to be nuclear fusion happening inside the star, and actually you get lots of free neutrons, and neutrons get injected into different cores. You make lots of radioactive elements. And so here I've got most of the things that give rise to most of the light. So in this explosion, you make these elements like cobalt 56, 57, and 60, also titanium 44, sodium 22, and so on. These are all radioactive and have different half-lives. And so here you can see cobalt 56 has the shortest half-life. Its contribution drops off fastest, right? Whereas here we can see the cobalt 60 has a much longer half-life. Its contribution lasts longer, but it starts out slower. And so we can look at what the shape of this curve is. So basically we've made all these things, and that's when you get to peak light, is when you've made all these things and they're all contributing photons as a result of their radioactive decay. But then they're all dropping off in brightness, but they're dropping off at different rates. So depending on the ratio of cobalt 56 to 57 to 60 and the other pieces, this overall total luminosity, the total brightness that comes from this radioactive decay, will vary. And so this is why there is a physical relationship between the absolute brightness and the shape of the light curve. It's because the absolute brightness relates to the mass of each of these things that are made, and that will change the way in which this slope goes down. And you've already seen this before, but this is how that then relates to different bands. So it's going to peak first in the UV, but then it's actually going to come up with a new peak in the infrared later on, and you can see how that happens. And that's where we're going to leave Type 1a supernovae for now, but we'll come back and talk more about binaries and mass loss very shortly.